Hey, we are moving to the flip the width hard version. This is from the CF round 1091 Dev 2. The question states that we are given with a binary array A of length n, okay, and k special indices p1, p2, pk, where pi lies between 1 to n, and it is given that the value ai of all elements at these special indices are same, okay. In one operation, I can choose a range LR where L is basically your left index and R is basically your right index of the range. And this is lies between 1 to n, basically in the array range, such that the range contains at least one special index. Okay. So at least one special index must be there in the range, and we need to flip all the bits. Okay, all the bits, right? Yeah, from the j lies between L to R. And we know what flipping means, like reversing the bit. Yeah. What is x here? It is the value at the special index that we choose before any one operation applied to be there in the range, right? So we need to find the minimum number of operations required to make all element of array equal to x. Okay. Here, each test contains multiple test cases. Yeah, that's a one general one. And the first line will be your number of test cases. We seeing that. The first line of each test case contains two integer n and k. Okay, n will be your length of array and number of special indices. The second line contains the array itself, and the third line contains k integer. That is the, you can say that, the list of special indices from 1 to p1 to p2. Okay, that's going to be lesser than equal to n. Yeah, obviously, because it is an indices of the array, so obviously it's lesser than like 1 to n. Okay, lesser than or equal to 1 to n. Yeah, and it is already given that a of p1 equal to a of p2 equal to a of pk, as we already seen here. So it is guaranteed that sum of n over all test case does not exceed 2 into 10 to the power 5. So maximum we can perform operation in O of n or O of n log n. O of n square we cannot do because it violates the limit of 10 to the power 8 operation per second. And the output here is the, basically we need to output the minimum number of operation required. So this is the output format here. Let's come to the logic part of it. Yeah. So the concept involved here is nothing but a difference array abstraction modulo 2, or we also call it as border counting technique. Okay. Uh, we know that in difference array, like we do the flicking approach. Like whenever we start the array at L, we start incrementing by +1. And whenever we encounter r plus 1, we decrease by -1, basically to keep track of a specific set of operation. But here it's not. Here it is the same operation we are doing, but in a different manner, in a border counting technique manner, you can say. So the logic here is that every block of wrong bit have exactly two border, one where the block starts and one where the block ends, basically your L and R plus 1, you can say. Yeah, so by flipping the bits of any range L to R, we need to make all element of array equal to a target element. Okay, so we are considering the sub case of it because the given question is the application of this only. So say the target element is 1. Now we want to convert this entire array element equal to 1. So let's see how we can do it. So if I see this test case, this is 1 0 1 0 0 0 1 1 1 0, isn't it? All right. So that's a 1. So if I mark if I mark the wrong set of bits, like wrong set of blocks, so this could be the one, this could be another block, and this could be another block. And if I show the border, so this is the border, start of the border, this is the end of the border, because we just say that every block of wrong bits have exactly two borders. So this is the one where the block starts, one where the block ends. Here also one where the block starts, one where the block ends. Here also one where the block starts, one where the block ends. And notice this is an invisible border because every set of bits, empty blocks, with have two borders, one where the block starts and one where the block ends. So we left out with this invisible border because if there is no border, we cannot consider this block get ended. So to follow the rule, we put the invisible border there. Okay, yeah. Now here the total number of border excluding invisible border is 5. And total number of border, if I include this invisible border, then comes 6, right? Now we are performing the operation to make entire element of array this equal to 1. So we are considering the operation L and R, basically the operation we try to perform. So here the L is 2 and R is also 2. So at index 2, there is a change, it become 1. It basically gets flipped, right? Because we know here the operation is that we flip the bits of any range L to R. So here it gets flipped, right? If I come to this 4 and 7, yeah, in the second operation, we applied on the range 4 to 7. So if you see 4 to 7, the bit gets flipped. Now in the third operation, we applied on the range 11 to 11. So if you see the bit here gets flipped. So total number of operation needed come out as 3. If I consider another test case 1 0 0 1 0 0 1, so this is the block of wrong bits, right? This is also. And if you consider here, this is the border border at start, border at end, border at start, border at end, right? So number of invisible border here is 0. No invisible border needed because look at this. This is the one separator. It caused the end termination of it. So we don't need any invisible border here because it does not come like this. The border end does not come like it is a empty. It is at the empty end, right? Not like that, right? Here after this also the element is there, so we don't need any invisible border, the border automatically comes in. Okay, so total number of border comes out as 4. Here we perform the operation at the range 2 to 3, so all the elements in the range 2 to 3 get inverted. Then we perform the operation on the range 5 to 7, all the elements in the range 5 to 7 get inverted. So total number of operation needed here to convert all the blocks of element to be 1 is equal to 2 1. Okay, so if I observe here, in general the total number of operation is always coming out as total number of border by 2. Look at this, total number of border by 2. Total number of operation is 6. Total number of border is 6. So total number of operation come out here is 3. Here the total number of border is 4. So total number of operation come out here is 2. So total number of border, if you see one more observation, then that also come out as always even because of the invisible border, right? So yeah, in general, total number of operation is total number of border by 2. And this concept we visualize here in this question. So let's come to this here. So if I see the extrapolation of this, so for a while, okay, yeah. If I see the extrapolation here, we are given with the special index, right? 149, let's say. Okay. And what is the situation that we need to consider at least one special index in the range LR, and then we perform the operation of flipping the bits. So we arise with two cases. Case 1, where special index is in one of the end of range LR. Okay. So if a special index is one of the range, it will perform operation in one wrong bit on block only, right? Because we cannot move in the other direction, right? But in the case 2, if a special index is in the middle of the range LR, then we can perform the operation in this bit wrong bit block also and this wrong bit block also. And you can see this is the basically borders shown by dash. So here also, like, this is the borders. Okay. Yeah. So if I perform the operation here, we'll take in the index range 5 to 14, and yeah, well, if you see, flipping happens in this range. So similarly for 8 to 10, like, you can match, like, it's just attaching. Similarly for 3 to 17, there's something happens, and 4 to 16, like, we're just flipping the bits, right? Similarly here, if you see 1 to 3, the operation performed, and then 1 to 2, the operation performed. So this is the one part of it. Now come to the case 2, because we want to minimize the number of operation, right? So we always try to choose case 2 if possible, because the advantage of this, that in one operation we will able to remove maximum 2 border, one from the current wrong bit and one from the other wrong bit. So that's what we written here. One operation removing one border from current segment and one from other. That could be the maximum case, or it might just remove one border from current segment. Yeah, that is the one. So since one operation can remove maximum 2 border, minimum possible value of minimum number of operation would be total number of border by 2, right? Exactly. Minimum possible value of minimum number of operation is total number of border by 2, right? Because one operation is removing maximum 2 border. But there is a twist, is this: if number of border in a segment is greater than minimum possible value of minimum number of operation, then initially what you did, you set the pairs, one from this segment and one from other, that get removed. After that, still we have a wrong bit in the current block. So it is like case 1 only. We're moving in only one direction, right? Exactly. Now we are moving in only one direction. So since it is behaving in like case 1, can you say that the total number of operation you need to give is the total number of border in this segment? Or can you say that in general, total number of operation you need to do is total number of border, total number of border, or basically we need to maximize the number of border. So maximum possible total number of border in a segment. Yeah, that's what we have written here. Minimum number of operation you need to do here is maximum total number of border in wrong bit block. In this case, exactly. But if you consider in general talk, then minimum number of operation is the maximum of maximum of both of it, like minimum possible value of minimum number of operation. And if this is get exhausted, then the maximum of total number of border in wrong bit block would be our possible answer. Okay, so let's come to the question and let's just code it, right? So back to the question part. So if I show you my implementation here, let's see how I did that. uh, Here it is. Basically, I taken the input. N is the number of elements in array, and k is your number of special indices. So that's taken. We taken the input of the array A here, right? This is the one you can see. Then the special indices we taken as an input. Now we taken the another container to keep track of that whether the index is special indices or not. So basically we are just marking that whether the index is special indices. If it is, then mark it as true. If it not, mark it as false. And since it is a zero base, so that's why -1 here. Okay. Yeah. So you can see, like as we debug, it's telling that one means the index is special indices, zero means the index is not a special indices. Okay. Now for keep track of current counter border, we'll use this. And this is the border container. Basically, it is containing the counter border in a segment. Okay. Yeah. Now we are iterating through the element of the array. So for this is to avoid like I greater than 0 because if we need to checking the previous bit, right here I -1. So to avoid this we are using I greater than 0 so that the overflow does not occur. Negative index we don't need to check, that's why. So if I is greater than 0 and a of I is not equal to a of I -1 means the last element, what do you say, like come to the question part of it, it means that it means situation like this. Okay, a of I is not equal to a of I -1 means we encounter the border, right? Yeah, that's what we are doing here. If a of I is not equal to a of ai -1, we are encounter a border, so we just incremented the counter border. And if index is the special index, then yeah, we encounter the one of the end. We are considering it like we are moving to a new block, right? Because basically it's like that. If you again try to show you, then it's somewhere like, sorry, it's somewhere like this. Yeah. Since look at this, this is the better example I can say. Uh, since you encounter the special index, so basically you are moving to the another block, right? Yeah. So that's why it's necessary that whatever the counter border we get here need to reset at 0 whenever we encounter a special index. So same thing we are doing here. We are resetting the current counter border to be 0 after pushing the counter border in the previous segment if we encounter the special index. Okay, exactly. And this is just like for the last segment, how many borders are there to push that we are using this. Okay, yeah. Now iterating over all the count of borders. So basically we want to fix the invisible border at the edge case, because look, if we know that one operation can remove maximum two border, right? Exactly. So we don't want this invisible border as we discussed, like uh, here, right? Invisible border, right? Total number of operation will be your total number of border by 2, right? Exactly. So total number of operation is total number of border by 2. But if the total number of border is 5 here, you will able to encounter the integer division error, right? You will get like 2 only. So that's wrong. So to solve this, we need to encounter, or we need to add the invisible border whenever we encounter invisible border. So like in general, we always get the total number of border to be even, right? Exactly. If the invisible border is not there. So same thing we are checking. We are checking that if the number of border in a segment is not even, it means that invisible border is there, right? So if the invisible border is there, we'll include the one invisible border in the current count of borders in a segment. So that's what we are doing here. basically we are checking that same thing. If the border count is odd, then add the individual border in the current segment. Okay. Now just the formality, basically the, as we discussed, what would be the minimum number of operation? So minimum number of operation would be your maximum possible value of minimum number of operation and the maximum total number of border in wrong bit block. Okay. So same thing we are doing. We know that maximum possible value of a minimum number of operation would be this total number of border by 2. So that's what we are doing. We are counting the total number of border and seal taking, like as we say here, look at this. uh, Total minimum possible value of basically minimum possible value of minimum number of operation would be total number of border by 2 seal we take, because to solve again the integer division. Let's say that if the total number of border is odd, then integer division we need to avoid, because the total number of border, there would be, let's say, one border, or we need to perform one operation where we need to remove one border. So to removal of it, we are taking the seal of it. So same thing we are doing. We are taking the, we are counting the minimum possible value of minimum number of operation. So first we count the number of border. Now we take the seal of it on division with 2. We'll get the minimum possible value of minimum number of operation. And another possibility that if maximum count of border in a segment is greater than minimum possible value of minimum number of operation, then the answer would be your maximum count of border in a segment. So for that, we keep track of maximum count of border in a segment, and therefore the minimum number of operation is basically either maximum of this minimum possible value of minimum number of operation or maximum count of border in a segment. Same we printed it, and same we get the EC here. Okay, that's it. That's the answer of it. Okay, so it's like a very interesting question. Interesting in the sense, like, because we never think about the border counting technique. Okay, in the difference array abstraction modulo 2. That's why I want to make this and discuss with it. So that's it. Thank you.